Okay. So, we are looking at the Gauss elimination process, and we just started discussing about the elementary matrix, and let us continue what we were talking about the elementary matrix here. So, here you can see when you do the row operation. So, the process actually what you have done, this is the row operation, that the first row operation that we have done, and that is what you get that first second row, and then when you do the operation of the third row, that is what you get it. Okay. So, now what we can do, we can similarly find out these things by doing row operations of the system. So, this is the matrix, and when we did that operation, first row operation, we get this, and so this is the elementary matrix. So, it is 2 1. So, that is what it gives the first things. So, this is 2 1. So, what we can have essentially, that means the other one would be E32 into E21 into A, which will give us the upper triangular matrix, or one can write E32 E21 into A. So, this is called the associative property of the matrix. Okay. So, now the other matrix which will come on the way is the permutation matrix. Okay. So, what is the permutation matrix? It is just like, let us say we have A, B, C, D. So, it can be multiplied with the permutation matrix, so that we will get C, D, A, B. So, let us say we can then multiply it with this another 2 by 2 system, which could be 0 1 1 0. So, this guy is called the permutation matrix. Now, this can be multiplied on the other side of the system, for example, A B C D, and let us say 0 1 1 0, then it will become B A D C. Okay. So, point here is that the left hand multiplication changes row and right hand multiplication changes columns. So, this is important here, that left hand multiplication changes rows and right hand multiplication changes columns. Okay. So, this follows non-commutative nature of matrix multiplication, which is A V not B A. So, this is called the non-commutative nature of matrix multiplication. So, the process of elementary matrix generally goes from left to right, which makes it easier to find the inverse. For like we had E32 into E21 into A is upper triangular matrix. So, if we try to find out A, this would be A, this would be U, E32 inverse, E21 inverse. So, inverse will exist as all column vectors are linearly independent. So, this is important. Inverse will exist if all column vectors are linearly independent. and we have seen through some simple example of 2 dimension and 3 dimensions how they span, whether they kind of independent or not. So, in that case what will happen is that A into A inverse would be identity matrix. So, what we will write ae02 inverse into A inverse is also identity. So, A inverse would be U inverse ae32 ae21. So, this is how you can find out that thing. Or other end you had, so our ae21 was 1 0 0 minus 3 1 0 0 0 1. This is our ae21. Now, to get the ae21 inverse, which would be straightforward, so which is 1 0 0. So, it would be the other way sign 1 0 0 0 1. This will give us an identity matrix 0 0 1. So, you can see this is how it works. Now, we look at the matrix multiplication. So, matrix multiplication, what we do is that A, which is n into m, B, which is m into p, C, which is n into p. So, least number of conditions that needed to be satisfied, which is number 1, number of columns of A would be number of rows of B. Second, Cij would be summation of k to m Aik Bkj. Other possible ways to do matrix multiplications: column multiplications approach, where let us say let B1, B2, Bp are columns of B, and C1, C2, Cp are columns of C. Then we can write A dot B1 equals to C1, A dot B2 C2, that means A dot Bi is Ci, in generic form one can write. So, here the columns of C are some linear combination of columns of A. Now, if we go row multiplication approach, which is like let us say Ai, where I goes 1 2 to n, these are the rows of A. Then we can write Ai dot B also Ci, where I goes 1 to n, and where Ci is the ith row in C matrix. So, again C rows of C are linear combination of rows of B. Now, if you let us say columns of A and rows of B, that is the way if you multiply it. So, like 1 2 3 minus 1 3 plus 4 5 6 0 minus 2 which is minus 1 3 minus 2 6 minus 3 9 plus 0 0 0. So, that will get us minus 1 minus 5 minus 2 minus 4 minus 3 minus 3. So, that means C would be summation of I to M A I B I, where A I ith column of A and B I is ith rows of B. Okay. So, now there are other means that one can find out is the block multiplication approach. So, here in the block multiplication approach, you can do the multiplication in that fashion, in block wise, like A1, A2, A3, A4, B1, B2, B3, B4, where A1 B1 plus A2 B3, this should be A2 B1 A3 B1 plus A4 B3, this would be A1 B2 plus A2 B4, A3 B2 plus A4 B4. Okay. So, now this is what you call it as a block multiplication. Now, if you talk about inverse of a matrix, there are in general there are two inverses. One is the right inverse, which it call like AR is identity, where AR inverse is the right inverse, or you can have left inverse, where AL is identity, where AL is left inverse. Now, one can note here, for symmetric matrix both the inverses are same. So, for symmetric matrix, AR inverse is same as AL inverse. Now, when you talk about inverse, so there would be another question which may come: how do we guarantee that inverse actually exists? So, one can say that inverse exists if and only if number 1, determinant is not 0, that means is not equal to 0. Second, all columns are linearly independent. Now, for a non-zero vector x, for non-zero vector x, if Ax equals to 0, then the matrix is not invertible. So, this is what it means, that means the columns are not linearly independent. So, you can take an example like let us say A is 1 3 2 6. Okay. So, there exists a vector which is like 3 minus 1. Then if we do A into x, which is 0. So, which means A inverse does not exist. Okay. So, now if A x equals to 0, then A inverse A x would be also 0, which means x is 0. So, the main logic is that x has to be a non-zero vector. So, that is what is important. Now, one can say how to find A inverse, that is important. So, let us take an example again for where the matrix is invertible. So, let us say A is 1 2 3 7. So, here the matrix is invertible, then we can find out the inverse, and let us say the inverse is in terms of a matrix which is A B C D. So, we can write A B C D into 1 3 2 7, which would be identity matrix. So, just using the property of the matrix that A inverse A equal to identity. So, from here what you get, A plus 2B 1, C plus 2D 0, 3A plus 7B 0, 3C plus 7D equals to 1. So, which means B is minus 3A by 7, A minus 6A by 7 is 1. So, A is 7, B equals to minus 3, D 1, C minus 2. So, you can solve this. This is a simple algebra, one can solve it and you can get these things. So, point here is that if A, B, C, D, if this is multiplied with 1 2 first column, this will get us 1 0, and A, B, C, D, if it is multiplied with 3 7, this should be 0 1. So, this is what it actually does. Okay. Now, how do we get back that? This is one way to do that. Now, there is alternative way one can also handle the situation, like let us see if you augment the system. So, we augment the system. What we have here 1 3 2 7. So, we augment the identity matrix here and we do row operation, which is let us say R3 minus T R1. So, here what we get 1 3 0 1 and this is 1 0 minus 2 1. Then again we do R1 minus 3 R2. So, we get 1 0 0 1, 7 minus 3 minus 2 1. So, which means one can write here A I is I x. So, if I both side multiplied with A inverse, so this is AI is A inverse I x. That would give us identity matrix A inverse is A inverse x. Okay. So, what we have got here, this is the inverse of the system, and you can see when we do in the other way around it is the same. So, what are the elementary operations that has been carried out? The elementary operations which are R2 minus 2 R1 and R1 minus 3 R2. So, this guy, then my E21 would be 101 minus 2 and E12 would be 1 minus 301. So, these are my elementary matrices. So, my upper triangular matrix U would be U21 into A. So, U12, U21, A is identity. So, A inverse would be 1 2 2 1. Okay. So, this is how you can also. So, if you multiply the, so this is an important property and one can cross check here. If you multiply it, this is 1 2. So, this will give us A inverse. Okay. So, if you multiply the elementary matrices, that also give you the inverse. Now, there are some characteristics property which are there. So, number 1, AB inverse should be B inverse A inverse, which means B inverse A inverse AB is B inverse B I. If we write it down, which is not I. So, provided A is invertible, A can be denoted as product of lower triangular and upper triangular matrices. Okay. So, we can look at the same thing from the previous example. So, we had lower triangular matrix which is 1 1 0 2. So, you can see that, and then upper triangular is 1 3 0 1. So, this is L, this is U, that will give us 1 2 3 7, which is A. Now, what is L? L is 1 0 2 1, which is 1 0 minus 2 1 inverse, which is E21 inverse. So, this is the my elementary matrix E21. So, I can write A is E21 inverse into upper triangular matrix. Okay. So, my L would be A21 inverse is the lower triangular matrix. Now, an invertible matrix can be decomposed into a lower triangular, diagonal matrix and upper triangular matrix. let us say we have this guy like the same example where we have 1 0 2 1 1 3 let us say we take 1 0 2 1, we take 2 3 0 1, which is let us say L 1 U 1 is 2 3 4 7, which is A. Okay. So, here this A one can represent like this guy can be written as 1 0 2 1, then 2 0 0 1, then 1 3 by 2 0 1. So, this should be lower triangular matrix, this is diagonal matrix, and this is upper triangular matrix. So, what essentially one is writing A is LDU. Now, here again little bit or more algebra one can do, which will get you 0 2 0 4 1 into 1 3 by 2 0 1, this guy is LD, this is U. So, the conservative solutions, they do not work for millions of unknowns. So, thus for those kind of problems, these kind of decompositions are highly required, because we cannot do this kind of the kind of conservative approach. So, for example, if you look at the operations of a 3 by 3 system, what you get? You get here is A, then finally it boils down to upper triangular matrix. So, first thing would be elementary matrix of 2 1, then elementary matrix of 3 1, then elementary matrix of 3 2. So, this is what it going to give us U, and what it will give us A would be, now to find out A, we get E 3 2 inverse, 3 1 inverse, 2 1 inverse multiplied with U. So, this one can think about is the lower triangular system for 3 by 3 system, for 3 by 3 matrix system. Okay. Now, if you have 4 by 4 systems, then or system, then the lower triangular would be, you can think about the lower triangular like first would be 2 1, then 3 1, then 4 1, then E 3 2, E 4 2, then E 4 3. The inverse of that, this would be the essentially the lower triangular system. So, now you see when there is a increase in the unknown, so the matrix size also go up, and when the matrix size go up, so this lower and upper triangular decompositions are important. So, the point here one has to note that when the system becomes really large or the unknowns are quite number of unknowns are quite high, then the conservative decompositions actually is not a very viable solution. rather this kind of decompositions through lower triangular and upper triangular matrix is quite handy, and this is what is desired. And this exactly this situation you will see when we will be looking at the numerical point of view, how to decompose the matrix and get these systems and how to get actually the solution. So, we will stop the discussion here and continue the discussion in the next session.